So first up in this session, we have Joe Cutler, who will present how we can extract recurrence relations from functions for amortized analysis.
Hi, I'm Joe Cutler. I'm an undergrad at Wesleyan University in Connecticut, and this is joint work with my advisor Dan Licata and Norman Danner. So, if I handed you this code for merge sort and then asked you to write down a recurrence for its worst case execution cost, you'd probably end up writing down pretty much exactly this expression right here. But the thing you did in your head to get there is actually pretty subtle. It required knowing things about the sizes of results of functions, like the fact that split splits a list in half, and abstracting lists down to just their lengths. And even more importantly, as a PL person, you might even have an operational semantics for the language that this function is written in that precisely defines the cost of program execution in terms of beta readx's or some other cost metric. And how do you know that this recurrence you wrote down has anything to do whatsoever with those formal costs? So, in other words, how do we make this informal process of recurrence extraction formal and ensure that it's correct? Well, at ICFP 5 years ago, the other two authors of this paper, and their co-author, presented an answer to exactly this question. And I guess rather than keep you all in suspense, I'll just show you what they came up with. So, recurrence extraction is formalized as a language-to-language translation. So given a term in some source language, we can translate it into a language that we call lambda C, which is a language whose terms are syntactic recurrence relations. Now, the overall idea of this translation, which we often call formal recurrence extraction, is to translate terms to output their evaluation cost, along with the size of the result. So, a term of type A in the source gets translated to a pair, consisting of the cost to evaluate that term, along with the resulting value, the size of the resulting value of type A. Now, this size translation that I'm talking about is essentially the identity on values, but except at higher type. Where the size of a function is a recurrence in the traditional sense. So it's a function from sizes to costs and sizes. Now, the real meat of this recurrence extraction is the term translation, which is defined compositionally by recursion over raw syntax. So given a term in the source, we can just translate it to a term in lambda C. Now, if you're a monadically minded person, you might recognize all of this as being a monadic translation into the writer monad. And all of this helps motivate the definition of the size translation. Arrows in the source become Kleisli arrows in lambda C. So we've extracted recurrences from the source language into lambda C, and now we need to prove that this extraction procedure is correct. Otherwise, all of this is no better than just extracting recurrences the old informal way. So the first step here is to fix an operational semantics for the source language, which is indexed by execution cost. You can read this judgment as M evaluates in n steps to V. And then we prove this following theorem using a logical relation. So for any closed term M of type A, if M evaluates in n steps to V, then the extracted cost of running M is an upper bound on n, and also the usual logical relations value relation nonsense. But anyway, this theorem is the crucial step. It formally connects the operational cost model to the extracted recurrences. One important piece of the informal analysis that this translation doesn't take into account is size abstraction, like, say, analyzing a function which takes a list in terms of its length, or a tree function by depth, or something like that. Now, we do this abstraction using a denotational semantics from lambda C into partially ordered sets, and this means that the objects that we get out are the standard objects you'd recognize as recurrences. You can compute closed forms and asymptotics and stuff like that. Okay, that was a lot of technical detail, I acknowledge that, but luckily all this has all been done before. And in the years since this technique was developed, it's been employed to formalize recurrence extraction for increasingly realistic languages, from the simply typed lambda calculus to inductive types, all the way up to PCF and ML-style let polymorphism. But all of this prior work is limited in the kinds of analyses they can handle, only ever worst-case cost analysis. And in many cases, worst-case cost analysis simply isn't enough to get tight bounds. And a technique like, say, amortized analysis is required to get better bounds. And so in this work, we extend the recurrence extraction technique to handle amortized analysis. So in the paper, we go over two standard examples of amortized analysis to demonstrate the effectiveness of our technique. And the first is a simple binary counter, and the second is splay trees as presented in Okazaki. Display trees are notable because they aren't really well handled by automated amortized analysis techniques such as resource-aware ML. And since the analysis of display trees is really complicated, I only have like 10 more minutes, I'll use the binary counter as a running example to motivate the way that we made our paper's main contribution. So consider a binary number represented as a list of bits with the least significant bit at the head. We can define an increment function in the standard way. Note that if the least significant bit is 0, the increment is constant time. But if the least significant bit is 1, we have to make a recursive call down the tail. Then we can define a set function which just sets the counter to a natural number value by looping increment n times. So here are the recurrences that you'd expect to get from these functions using the informal method. By the way, for the rest of the talk, we'll fix the cost model that cons operations are the only cost of the operation, and they each incur one cost. So these two recurrences here solve to tinc being linear and tset being n log n. But this actually isn't a tight bound for set. It's actually linear. Intuitively, this is because the constant time case of the increment happens way more often while you're looping, but you have to take the max between the two non-empty branches when you extract the recurrence, which makes it look like increment traverses the whole list every single time. And unfortunately, this is exactly what the prior work in formal recurrence extraction would do to this example. To motivate some stuff down the line, let's take a look at how that would go. So we can take our increment function written in the source language and pass it through the recurrence extraction translation to get a function into a pair C cross, which computes the cost of running increment along with the size of the result. Now, the first component of this pair is the important one. It's the execution cost. So I'll just write that with the subscript C. Now, this syntactic recurrence that you get out is exactly what I hope you'd expect. The key case is when the least significant bit is 1, it costs 1 for the cons, plus the cost of recursing down the tail. Now, after this, we use the denotational semantics to interpret this recurrence as a map between posets. Most importantly, we interpret the bit list type as the natural numbers, which abstracts a list to its length in the traditional way. Now, the monotone maps of posets we get in the semantics represent the exact same loose bounds that we talked about before. If you carry it all through for set, you still get n log n. So, we've seen how the previous work comes up short. Now let's take a look at how the amortized analysis of the binary counter actually should work to help inform how to change the recurrence extraction to get the tight amortized bounds we're looking for. So here's a quick refresher on amortized analysis for those of you who've forgotten about what the big deal was since you last learned about it. So amortized analysis comes in a few different forms, but all of them boil down to essentially smoothing out cost across program execution so that when you analyze repeated executions of the same function, they don't all look like the most costly one and instead look like, say, the average one. And the approach to amortized analysis that we take in the paper, which is usually called the banker's method, is to maintain an invariant of imaginary credits on the nodes of a data structure. So these credits incur a cost to create, but then you can spend them to decrease cost. And by passing these credits around the program, you can rearrange costs. The credit invariant for the binary counter is that we keep 1 credit on each cons cell, which holds a 1 bit. So here's an example to illustrate how this works. We start with an empty counter with no credits, and then the first increment flips the first bit, and we spawn a credit to put on the 1. Total amortized cost here is 1 cons plus 1 created credit equals 2 amortized cost. And then the next call to increment flips the first bit from 1 to 0 and the second bit from 0 to 1. And then to reestablish the credit invariant, we spawn a credit to put on the new 1 bit, which incurs a cost of 1, but then that's canceled out by spending the credit which used to be on the least significant bit. Again, total 2 amortized costs. This is the essence of the analysis, and you can convince yourself that in every case, the amortized cost of increment is 2. So in order to do this kind of analysis by recurrence extraction, we need to make these credit policies expressible in the source language. So to that end, we extend our source language with credits to make a language that we call lambda A. So lambda A internalizes everything you need to express credit invariance in your code, and it comes in 3 main parts. So first, we need to be able to track the credits using the type system. So this new typing judgment says that M is a term of type A in context gamma, which can use up to C credits. Now, since we don't want credits to be duplicated and then the same credit spent twice, the type system is affine, which means that variables can be used at most once. So next, we need to be able to attach these credits to terms like, say, the elements of a list. And to do this, we add a modality to the language. The terms of type bang CA are morally terms of type A that carry C extra credits. And the intro and elim rules for this modality are actually pretty intuitive. The intro rule says that if we have a term M of type A and we have C extra credits lying around, and we don't need to construct M, we can just attach them to M and get a term of type bang CA. And the elim rule says that if we have a term of type bang CA, we can peel the credits off the term and allow them and the value to be used in a continuation to make more stuff. So finally, we need the ability to create and spend credits, of course. And the create rule here says that if we have a term which uses A plus C credits, we can simply create C of them. And dually, the spend rule says that if we have A plus C credits, we can spend C of them and then use a term which only requires A credits. Now, all of these changes I just described are completely local to Lambda A. We don't change the recurrence language at all. It's still fully structural and has no modality. So, we've extended the source language with the features that let us formally specify these credit invariants in our code. Now let's take a look at how the binary counter example would actually get encoded into this language. So, in Lambda A, we redefine the bit type to be unit plus bang1 unit. A bit is either in left of a unit, which represents 0, or in right of a unit with 1 credit attached, which represents 1. And then the code for increment has the exact same behavior as before, it just maintains the credit policy. If the list is empty or has 0 as the least significant bit, we create a credit and make a 1-bit value by attaching that credit to a unit value and then returning that as the least significant bit. And if the least significant bit is 1, we detach the credit using transfer, spend it, and then make a recursive call on the tail and cons a 0 onto the result. So, all good, Lambda A can express the credit policy that we were looking for, but now we need to actually extract recurrences from it. But the recurrence extraction for Lambda A is actually quite simple. So let's briefly recall that the recurrence extracted from a term consists of a pair of the cost to compute the term along with its size. So since creating A credits incurs a cost of A, we just add A to the extracted cost. And dually, we subtract A from the cost component when we spend. Now, since the credits, as I mentioned earlier, aren't present in the recurrence language, the extraction has to erase the modality in its corresponding form. So save gets erased completely and transfer gets turned into a len. All good. So now that we have the recurrence extraction in place for Lambda A, let's extract terms for recurrences for the binary counter, solve them, and hopefully get the type bound we were looking for. So above line here is the term for inc that we wrote earlier, and below I've written the cost component of the recurrence you get in Lambda C for this term. So when the argument to this recurrence is empty or has 0 as the least significant bit, increment costs 2. 1 from the cons, 1 from creating the credit. When the least significant bit is a 1, the cost we extract is simply the cost of the recursive call. Now, why is this? Well, we do one cons operation, which costs 1, and then we spend a credit from the least significant bit, which subtracts 1. So we're just left with the cost of the recursive call down the tail. And it's super easy to see that this function is 2 everywhere, and indeed the monotone map of posets that it denotes is in fact the constant function 2. So carrying this all through for set, we get that the corresponding mathematical recurrence is order n as desired. So, we have a recurrence extraction procedure that extracts tight bounds for amortized analyses, and the final step here is to prove a theorem like the bounding theorem for prior work, which connects these recurrences to the operational semantics. And similar to how we did it in prior work, we first define a big step operational semantics for Lambda A, but this time indexed by amortized cost. So this judgment reads that M evaluates to V with N amortized cost. Then we use a logical relation to prove the same bounding theorem as before, but this time the cost we're bounding is an amortized cost. But the crucial consequence of this theorem is that for closed terms, the amortized cost that we get for the recurrence is a bound on the actual execution cost. And so, for example, the set program isn't just linear in this strange cost metric where we can subtract and add arbitrary costs. It actually does a linear amount of cons operations. So in summary, we formalized a process of doing amortized analysis by recurrence extraction. Given an amortized analysis of a data structure, such as a binary counter or splay tree written in Lambda A, we can automatically extract correct recurrences into Lambda C. This extraction procedure has been proven correct and is expressive enough to handle non-trivial analyses like splay trees. Thank you very much.
Thanks, Joe. Now in both the New York and Asia time bands, you should be able to click a link in the sidebar in Clowder to be able to access the Q&A sessions.